Ah, perfecto.
Y en verde desaparece el simbolito de diámetro. Mira la esquina inferior izquierda. Aparecer.
Ah,
Y se desaparece. Entonces, cuando está verde, uno aprieta acá y se está activado el micrófono, apretando el botón del.
happy to have here Professor Lucia Duarte from Universidad República de Uruguay. Professor Lucia Duarte is an international recognized expert in beyond standard model physics, and especially in the implication of several DSM extensions in collider physics, dark matter, different realization of effective field theories in new physics processes regarding colliders and regarding neutrino physics and dark matter. And today, Lucia Duarte will tell us about sensitive of SMEFT affecting interaction in the agnostic regime. You can start, Lucia.
Thank you very much, Antonio. I'm so glad to be here. Thank you very much for your hospitality and for letting me tell you about what I've been doing. So this is not a very formal talk because I had not much time to prepare it. I'm going to show you some new results, work in progress, in fact. But I'm really glad that people are aware of what I'm doing right now. So the talk is called Sensitivities to New SMEFT Interactions in the Agnostic Regime. So I'm going to tell you what I'm saying here and what I've done in the last years. So let me tell you what we've been talking about. I'll show you a bit of my motivation to construct an effective field theory with right-handed neutrinos. Then we will discuss a bit about the new SMEFT operators and how we take care of a simplified scenario that I'm calling agnostic, and tell you why and how we do that. And then I'll tell you about work that we're currently doing with Agustin Guillerea, my master student, that it's a recast of a heavy neutral lepton search that has been done by CMS in the last years, in 2023, and how we got from there the first LHeC bounds on this agnostic scenario for the neutrino standard model effective field theory. So then I'm going to compare those new results with previous results we had on sensitivities of future colliders to this kind of signals, and you will let me know what you think. So let's see, masses in the standard model, as you know, are generated when the gauge symmetry from the SU2 left and U1Y groups break into the U1 church group. So the Higgs doublet takes a bell, and we have the Higgs field there, and every guy who has a mass gets it from the Yukawa Lagrangian, mixing the right-handed part and the left-handed part of the field. So everybody here who gets a right-handed and a left-handed component under C2, you get a mass, but neutrinos in the standard model have no right-handed component, and you have to add them in order to get a Dirac mass for neutrinos. So you guys are students.
Yeah.
You know this?
Yeah.
Yeah? Are we sure? Because you're here and I can explain. You don't. You don't look like you know this. Ask something. Because I'm here and I'm just to explain.
I want to know where to start.
You know what to ask. Okay, I go on, but then after you tell me something, because you know it's 5 people here, so I'm gonna come to people here because that's why we are here to learn. So you don't have right-handed neutrinos in what you call the standard model in principle. So you don't get this mechanism, this Higgs mechanism to make a mass. And the standard model needs to be extended to include neutrino masses because of this. So you can do that, and the easiest way to do it is what we call the seesaw mechanism type 1. So you put a right-handed neutrino for every left-handed neutrino. Here you have the flavors written, but you can think about it in the gauge basis. And then you write something that is Lagrangian, which includes kinetic term for these right-handed neutrinos, and call them big N so that we don't get confused. So big N's are the new ones, and little n's are the old ones, the standard model ones. Okay? You you're my guy, so I'm talking to you because everybody here knows everything. Okay, so then you can write this term, which is a Dirac mass term that I was talking about in the last slide. Here you have, I have written it with charged leptons, but here you can build the same thing with the right-handed neutrinos. And after this, the symmetry breaking, this guy gets a bed, and then you have the Dirac mass I was talking about, but mixed with the left-handed component, that is the standard model left-handed component, and the new right-handed component, and you can write this mass in terms of these y's. And you can, because this guy is a right-handed neutrino and has no charges under the standard model symmetries, you can write another mass term. Do you know about that? So this is a Majorana mass term. You know this. Cool. So you know everything. Yeah. Well, and then you write this. This would be Dirac neutrinos only, and when you add this term, you get the Majorana neutrinos, and you diagonalize your mass matrix, and you get 6 massive states, 3 light neutrinos, which have masses proportional to this Dirac mass to the square, but divided with this mass scale from the Majorana term. So this is why they are light. You say this mass should be of the kind of masses of the leptons, like electron mass. So this is little. And you divide it by this guy, and then you say, well, the bigger this guy is, the lighter the neutrino, the light neutrinos are. Okay? And that's why it's called seesaw. And then you get the 3 heavy Majorana neutrinos, which will have a mass proportional to the Majorana mass scale. Okay? Well, something like that. And this can be done in many different ways with very fine tuning, and you can do many things here, but this is the main idea to consider the simplest way to do it. Okay? You work on this? You know this? Okay? Okay? Perfect. So that's it. You can do that. Yeah.
What about a sterile neutrino?
Yeah, you can call it sterile.
What is it?
This is the right-handed guy. This is the sterile.
Okay.
It's sterile because it has no standard model charges. So it's electrically neutral, but it has no hypercharge. The guy wouldn't interact with anyone else except for the mass terms. You don't get it to interact with anyone. And then when you make the mass diagonalization, you get the mixing, which is what I'm going to talk about right now. So I'm not doing all the calculation, but you will have this mixing of, which I call actile. These are the left-handed guys in the standard model. So these are the guys that interact with the W and the Z. Okay? And then you get the light ones, 3 light ones we have. Okay? And you can mix them with the actile state. So in order to score the light ones, you have to measure these guys, which is the ones that interact with the W and the Z, and then you get this mixing, which is like the Ponce-Corvo matrix, you know. Okay, you know what I'm talking about? No, not that much, because I haven't been so deep in my introduction. So it's like, or you know it, or I have to explain you right now. But in oscillations, what we measure is like measuring the life of these guys. You get mixed with the massive state, and that what makes the oscillations be able to be seen. So it's this mixing, this actile light mixing, that gives you all the phenomenology of the neutrino oscillations, because you have this left-handed actile states that are the ones you measure when you measure W's, and then they travel. And as they travel, in fact, the ones that travel are the massive states, because it's the massive states that propagate. You know that, no? Yeah. Okay, so you change bases, and this change of bases and the interference between the components of the 3 light massive states with each flavor of the left-handed guys is what gives you the probability to change oscillating depending on the distance from the production source, on the energies and all that. So have you seen that in somewhere
Yeah.
before? Okay, so that's it. Does it mean something to you?
Yeah.
Yeah? But you're saying yeah, like okay, don't bother me.
No.
But have you heard about neutrino oscillations?
Yeah.
Okay, so you're not that lost.
No.
No, I don't want to be like too much. Okay, and you're okay. You look very good. You work on this. No? Okay. You look very sure. Well, so you have the light ones, but you also have the massive ones, the heavy ones. So I'm gonna call this guy the heavy neutrino. So as we saw before, and I didn't say it, but the massive states, when you include a Majorana mass term in your Lagrangian, are Majorana states, which means that these guys are the same as I lost the term, the antiparticles. So they're the same level.
But you also said before that adding these terms, we are constructing a Dirac mass. So
we have a Dirac mass, but we have a Majorana mass too.
So
and given you put this Majorana mass term, the particles, the massive particles you get upon diagonalization of this mass matrix will all be Majorana states in the sense that they are the same as their antiparticles. And you could show you that, but I should write and do some calculation, but it's okay. I don't think we need to go into that, but this is for sure. Once you put this term, when you diagonalize this matrix, it has mu's and n's, and you try to get the massive states, you get these eigenvalues, but the states that are the eigenstates of the mass matrix are the same as their antiparticles. And that's for sure.
Or just the right-handed part?
The right-handed guy is right-handed. It cannot have a mass. It lives in another base.
Oh, yeah.
Okay? So we have sterile guys, which interact with the active guys, which are here in the doublet. So you can get these are the sterile, right-handed. These are the left-handed, which I call active, but this is not the massive states. These are the gauge states or interaction states, if you want to say. And then you have to diagonalize this mass matrix that I'm not writing because, sorry, I didn't do it. And the eigenstates of the mass matrix which have a value of a real value of a mass, those guys are in the bases and are like the light ones and the heavy ones. And you get 3 and 3. And of course, you can tune things to make differences between the 3 light guys and the 3 heavy guys. But that's what you will get. So you were asking something? No, before. What was your initial question? Because I got lost.
I didn't so as clear that what was the reason of why neutrinos were just Majorana.
Yeah.
No, a mix between a Dirac particle.
You can make them quasi-Dirac.
Yeah.
And then you heard about that. So that they are Majorana, but not that much. And you have that depends on the difference between the masses.
Oh, okay.
And you can play with that to make them like what we mostly do, that is making them quasi-Dirac states.
Okay.
And that depends on the difference of the masses of the light guys, and then you can play it again more or less like that with the heavy states. So that's what you're thinking about.
Okay,
cool.
I see.
But
so
they are, if you put the Majorana mass term, they're Majorana. They can be not that much Majorana, and those are like the quasi-Dirac states. Okay. Are you learning something? Yeah? Okay, cool. That's the point. So these light states are the ones fussing around with neutrino oscillations. And these heavy states, it depends on how heavy they are, will also have a mix with the active states that we measure with the W interactions in the experiments, okay? So this mixing matrix will give you, well, how much you will get of the heavy end when you play with the active left-handed guy in the standard model, okay? And you have many experiments testing this mixing. Okay, this is the, for instance, I have put a plot of the mixing between the electron neutrino and heavy neutrino. You can say one of the three is lighter, so we can choose the lighter one to be the one that really interacts, and put the other in with a mass that you cannot produce or think about them, and you can do that. Okay. Okay, so this has been tested in many experiments, and well, you have here all the curves from every experiment that puts bounds on how much this mixing can be, given that we don't discover the heavy Majorana neutrinos at all, because we haven't seen them. No, we're talking about particles that we don't find. So sad, but it's true. Okay. So how much we don't find them? This is a plot. And you can plot many experiments. There are plots with prospects. So this is not the newest one, but it's one that is clear to see that the scale of the actual mass of this guy has been tested from 10 to the minus 9 GeVs to thousands of GeVs. Okay, so I'm going to be talking about like this part of the plot, but there are many experiments putting bounds on that. So these are not the strongest, but I like this plot because it's kind of clear of what's going on. Okay, right. And this mixing square, which is what I'm plotting here, what is plot here, scales as the mass of the light neutrinos over the mass of the heavy neutrinos, something like that. So that's it. And experimental bounds are around like what I was telling you, 10 to the minus 5 here for a mass of heavy neutrino from 100 GeVs, something like that. Okay, so this is little. Maybe it's too little to discover them, and it's good. We don't see them, and we won't see them, and we kind of have a prediction that goes that way. So the lighter the light neutrinos go, the heavier the other ones need to be. And you have these experimental bounds. So okay, this is not very encouraging. So one question you can ask is, given that this is the source we have of lepton number violation, I haven't mentioned this, but if you do all this stuff, you will have predictions of Majorana neutrinos being coupled in ways that you can violate lepton number, and this is proportional to the mass of the Majorana magic scale. So that's why they break this symmetry. And you can say, okay, I won't discover lepton number violation because this meeting is too low, too little. Okay, so when I was a student, a PhD student, before that, so when I was starting my PhD, there was this question of, are we going to be able to see lepton number violation if it's only caused by the heavy Majorana states, and you can only find it through the mixing with the active states? Is it all? So that was a question. And from my point of view at that time was, okay, no way. I want to work on this because this is too little to be seen. So I won't waste my life on this. But I ended up like working on this. But this is a question that I always was asking me, and Claudio has seen me giving talks before, asking myself this question many years ago.
Something similar happened to me in my thesis too.
Yeah, so you see this and you say, okay, no, this is for sure, this is lost time. So okay, but there are some tweaks you can do. So we will start talking about that. So, okay, let's play another game. let's say we have to put the right-handed neutrinos with the standard model fields in order to get a mass. Okay, we have to do that. That's okay. So we write the renormalizable Lagrangian with this type 1. I'm choosing type 1 seesaw because it's the easiest. So this type depends on what you do exactly to get the mass matrix and which fields can make this happen. So I'm not discussing that because that would get me like a whole course on this. But you know, things can be done. But let's take this easiest one. And you say, okay, I have the standard model and I have this Lagrangian that I was writing right here with the Dirac and the Majorana master. Works.
That's your question.
Yeah.
Can you go back to the, So this expression of the mixing, where is m nu over mn, where m nu is the mass of the neutrinos we know.
Yeah.
So this is type 1.
Yeah, this is type 1 so relation.
Actually, if you put as a mass of the neutrino, say, I don't know, 0.1 electron volt. Yeah. And then you put Mn as 100 gig electron volts, actually the mixing that you get is much more than the bound of Atlas.
Yeah. Yeah. So this line is called the seesaw floor.
Oh.
That's it. That's the line you get from that equation, which is the naive prediction. Just playing with Dirac mass and Majorana mass to give mass to the light neutrinos. This relation that I have here, you substitute this mass and then you play that and you get this line. So this is the theory prediction. We're above the measurements of the theory prediction. So that means that you can really play with the coefficients and with the mass matrix and doing things in order to get a higher mixing. So you can do that, but experiments are not finding like evidence of a higher mixing. That's it. Maybe that's okay. That's
what I meant. Yeah.
Okay, perfect. Yeah, that's this line. I had forgotten to show it. Thank you. So let's play an effective field theory. So we say, okay, we have these right-handed guys, and I can put the standard model, the renormalizable Lagrangian, and start building an FT, an effective field theory, with these new fields that I have to put in my model anyway, because if no, I don't get any mass, not Dirac, not Majorana, or whatever. And I say, okay, I put them, and I start building an FT, thinking, okay, we have some scale where new physics happens, that will give me some new interactions that I can see right here. This is the electroweak scale, but here is like the atom scale. And then you say, okay, if something else is going on in a UV completion that has an energy to produce new fields that are very massive that I cannot produce, but I could somehow try to find an evidence of these imprints in my experiments at my energy, which is like, okay, let's think about LHeC, for instance. Okay, so I try to catch that information, writing higher dimension operators that depend on this new physics scale lambda, which you can think of as the mass of the new fields that I should include in order to see some kinds of interactions. Okay. And well, you can build operators. So you can play with dimension 5. You can put the Higgs field here and 2 right-handed states and build this operator. Or you can also put 2 right-handed guys, but with a sigma mu. This is a tensor interaction, and you can couple them to the B mu, to the field strength of the Y hypercharge, which has the photon in it. Okay, know this guy? You? B mu, you know who this is? Okay, perfect. And you can do that. This operator, for instance, if you don't have different right-handed neutrinos, if I can be different from J, as the sigma mu is antisymmetric, goes to 0. So you need to have at least 2 heavy states, two right-handed heavy neutrinos. I'm gonna call them heavy because I'm gonna be like coupling them in the next slide. So sorry, I'm talking about the future for you. But okay, if you don't have two of them different, this one you can't write it because it goes to 0. And then people used to write here this binary operator, which is a dimension 5 operator, but only has standard model neutrinos in the left-handed doublet. So this is not what I would call it's in the new SMEFT, but not in the NR SMEFT, okay? Because it's an effective operator, but it hasn't an explicit right-handed neutrino there, okay? But we can talk about it. So there it is. So I'm citing some people who have done this exercise, and you can go on and build dimension 6, 7, 8 operators, and you can treat this effective field theory as the standard model effective field theory, but including the right-handed fields. So indeed, what we should do is taking this seriously and couple this to the standard model effective field theory with only standard model fields, and put them in for every dimension, write all the operators, the SMEFT operators and the new SMEFT operators also, because if we assume that this mass comes from the presence of this right-handed component of the neutrino field, you should do that. That's what would be the fair play, okay? Well, what am I doing? I am simplifying things so much, okay? Very much. Why? Because I need to work. I have to pay my rent and all that. So I cannot be doing so complicated stuff as Antonio likes. I'm gonna try to do a simple thing, okay? So that I can teach it to my students also. So I'm gonna build an effective theory with only one right-handed neutrino, not 3. Okay, I put just one. That ruins oscillations and all that. I cannot describe that physics, that low energy physics, okay? But I'm thinking about collider experiments and all those things. So I say, okay, I put just one right-handed neutrino, which will need just one heavy massive neutrino, and I will try to see if I can find it. Okay, that's my plan. Yeah.
In the last slide, you mentioned that you need at least 2 right-handed neutrinos
to have this operator at dimension 5.
Yes.
If you don't have it, you don't write it.
Yes, but this happens only for dimension odd operators.
Yeah.
You need at least 2 right-handed neutrinos. For dimension 6,
it's only for this operator because you have the sigma here. This one you can write it with I being the same as J. Yeah. So I can write this guy, but I cannot write this guy if I only have one right-handed neutrino in my basis.
Yes.
Okay, that's it.
Dimension 6, you don't have
basis. You have something similar.
Only one.
Yeah, but you don't have it with, that's it. Exactly. Okay. So what am I gonna say? Okay, if the mixes were so little, I'm gonna just discard them. I'm gonna say, okay, if I discover something, it's not because of the mixing of the heavy state with the light states. I will say, I will ensure that if I find something with the predictions of this kind of model, it is caused by some other physics, okay? Because I'm neglecting the mixing, okay? Why do I do that? Because it's easier. So I'm not gonna lie to you. It's because I should. If not, I have to do the mixing, calculate the stuff, and as you see, you can fine tune that thing. So I would need a very specific way to see what kind of seesaw I'm calculating in order to see how the mixing goes and all that. So I don't want to do that. I'm saying, okay, if this is little enough, I'm gonna neglect it. Okay, but it's a decision, and we're gonna see that it's not a good decision.
So how do you couple your new N to the rest of the standard model?
With the operators, with the dimension 6 operators.
With the dimension 6?
Only with the dimension 6 operators. Yeah.
Okay.
I say the only coupling with the real world comes from here. Is the standard model. I have the standard model, and I have these guys, and I'm neglecting everything in the middle. Okay, so it's a simplification. It's not that I have an argument more strong that okay, mixings are very low by now, so I can say the contribution from mixing will be low enough so that I don't need to take it into account in my calculations. And if I find something, well, I will see that it's not given by the mixing alone. So I'm really thinking about, okay, let's discover new physics if it is there.
So it's
in
like,
a higher energy scale.
So it's like an exploratory method?
Yeah, totally. If you find something, then you will have to go and, in fact, look for a UV completion. That really is a renormalizable theory that has more guys in it that you can shrink to these effective operators when you lower your energy and you make experiments at LHeC energies, for instance. Okay, so it's the same play like at the SMEFT or the low energy theory of the standard model when you integrate out the W, the Z, and all that. So it's the same, how do you say, philosophy, but with these guys. And why do I do that? Well, because it is. So I'm going to think about the standard model and the dimension 6 operators I'm going to show you right now. And what I'm trying to explore is like this scale where the masses of the heavy neutrinos are 100-ish GeV, so here, and the scale lambda of the new physics is well above. So at least 1 TeV, okay? To get a number. So let's do it. I'm going to show you the new SMEFT operators of dimension 6 and what I simplify more, which is what I call the agnostic scenario, okay? So here we go. I just written the simplest vertices, but there are much more. So you can see, first, you can write this, what we call the Higgs dress mixing. This is because you have a left-handed and the heavy one, no? And you can get Higgs fields from every Higgs doublet here. So this is the simple one, N, nu, and H, but you can put 2H or 3. You can get one from every guy. So you can play with that. We are discussing this with Carolina these days. Okay, so you could write this guy with 2 Higgs fields, 3 Higgs fields, and you will have them there. Okay, and then you can have other operators. This one gives you what we call the vector boson currents, because you have the N. These N's here now are the right-handed field, but as the mass diagonalization, I'm not talking about this, I say, okay, this guy is the massive guy, because if you throw all the mixing, that's what you get. Eh? You don't like it. I agree. That's good. You live on physics? You depend on physics for your life? Oh, okay. We'll talk about this later.
Later we can talk about it.
Okay. So you put these 2 ends and you can couple them with the covariant derivative in the standard model, so you get Z, W, and all that. But the ones that survive are the ones with Z, because you don't get any more. You can have a W here because it's charged, so that would violate charge and all that. So this is the one that survives, and you can also put 1 Higgs and 2 Higgs fields here because you can couple them to this kind of vectors. You can write this guy, the heavy guy, the light charge lepton, like electron, muon, etc. And again, you can write things that now are very similar to the standard model because you have the left charged lepton, the N, and the W. So this is like a right-handed vertex that is looks the same as the standard model, but with the helium, okay? And you can write these operators, which are dipoles, that you can build out of, well, this combination. This is the field strength of the W. Have to do the calculation here, have many terms, but the one that is easier is that you get a tensor operator mixing photons with neutrinos. And you will say, why? Why that? But yeah, you get that. You get that because you have the sigma. So this is a tensor interaction. Okay? It's like the magnetic moment of the neutrinos interacts with the photon. That's the physics behind it. Okay? You don't like it. Okay. Yeah. I don't like it either. Yeah, but you know, you can have charge coupling to the photon. That's okay, but you can have other structures. So this is the magnetic tensor. The magnetic moment of this neutrino that you could have. So this one, you cannot make them in a UV completion at 3 level. You have to build, when you have other heavy states that give you the UV physics that shrinks to this kind of vertex, you have to make loops. And if you have done some loop compilation in your life, you see that, you know, magnetic moments are things that come out from loops. So I had things like that with top quarks when I was younger, much younger, before my PhD, when I was in my master. So you can find this kind of. Okay, so and many more vertices that are like this way. And you can have 4 fermion interactions. You can write N, L, upwards, downwards with gamma matrices. This means that you would have a completion that should be mediated if you have another guy who shrinks this vertex to this expression with the 4 fermions. This should be connected with a vector because you have a gamma muse. So that depends on the Lorentz structure of the operator. Okay? Can you imagine that? Like D, U connected with some vector and this other fermion line N and L. So you could have this dot and I would separate it. Okay? Something like that? Yeah, I didn't write it because I didn't have time to show you much, but this is how it goes. And you can do this with 2 N's and quarks from the doublet or leptons from the doublet or the right-handed fermions here. And you can do the same, 2 N's, some vector, and the fermions. Okay? And you can think of UV completions that are vector mediated. That's why I wrote that. And you can have scalar mediated UV completions. So you can mix that Q, U, and L, and you get something like that. And then if you try to build a UV completion, you would put a scalar connected to 2 vertices. Okay? And you can take all the list. Okay? So this gives you lots of vertices. So this gives you lots of possibilities to study new physics because that's a lot of people playing. So anytime you try to write a process, you will get many diagrams. And then you can say, okay, I can do things at tree level or loop level, or no, you can start to play. So this is huge. This is huge. And now I'm going to tell you how I try to make things a bit more easy because it's huge. Okay, so you've seen every operator, we can count them, but you have 4, 5, or here, 4, no, it's like 5, 3, and 2, yeah, 5. These guys that give you many vertices. So this is already a whole fauna. Okay, so I'm gonna take an agnostic benchmark, which is I turn every operator on at the same time. So that's not what people do. People in SMEFT turn on one operator at a time. Why am I doing this? Because I want to see interference effects between operators. Because you don't know, if you have many operators that contribute to the same final state, for instance, you can play with interference within them. And there are signs that change, and you get a whole richness of things going on when you allow for different operators to be on. So I turn them on at all at the same time, but also because indeed you're writing one operator thinking about one scale, but when you do the running, the normalization group running of these operators between scales, they mix with each other. So you cannot say for sure that you have this operator on here and then you will have it in the same way in another physics scale, which is not that far. So if you want to play with things on LHC, but also try to figure out, I don't know, like meson decays, which is something that people have been doing, then you have mixing. So you cannot say, I start with one operator and I run it, and I will still have only that operator. So that's why I'm putting everything on. But to put everything on, you have to simplify somehow. So that's the agnostic part. So other thing that is good, that is you can allow for production of this heavy N from a kind of physics that is different from the physics that makes it decay. You can put one operator to produce it and other to make it decay. So that gives you richness. And well, you can do all that, but you have to simplify somehow. So what I see that is a doable thing is that you can consider every Wilson coefficient to have the same numerical value. So I put them all on, but they all have the same coupling value because I have to do numbers. Okay, so I put a loop factor in the operators that are only loop generated in the UV completion because they have to count less. So these things happen, but not that much because I know this happens less than in probability. When I get the matrix element squared and I see and try to make numbers, this should have a weight counting for the loop. And well, doing that, I have a simpler parameter space, which is the coupling, which I'm not calling C, I'm calling it alpha because of traditional stuff. It's like SMEFT it was originally written with alphas. The scale and the mass, and because I only have one guy. So I can plot these guys, like alpha and mass. That's perfect. Okay, so I'm going to tell you what I've been doing. And today it's a recast of a search that was done in CMS, looking for heavy neutral leptons, but we are translating it into this agnostic scenario. Okay, so and we can compare or avoid things we've done before. So here we go. We have collider bounds for the heavy neutral leptons coming from many searches by now, but like 3 years ago, I found this paper from CMS that what was interesting for me is that they were testing very heavy mass for the heavy neutrinos. They were exploring this kind of interaction with the mixing. So these V's are my U's from before, sorry, because I like U, but they call them V, but it's the same thing. So they were searching for this heavy N in processes which are proton-proton to muon-muon or anti-muon, and to jets. So this is spectral boson fusion. You can have the diagram for the type 1 CISO N here, and you can also make this final state with active neutrinos. This is a contribution given by the dimension 5 operator, but they were looking for both signals. But I'm gonna see this because I have the heavy guy. Okay, so they did it. So they make a search. Search is very complicated. Okay, so what you have to do when you try to follow a search and try to say, okay, these limits they find for the mixing, how can I translate it into my operators? Okay, my everyone on operators. Okay, so what we have to do is generate processes with our theory and try to make them all the cuts that they do in the search in order to see in the end what I find, which number of signal events I get, and then put bounds on the coefficients of the effective operators. Okay, that's what my student Agustin does. That's not me, that's him. So the plot in the search is here you have all the backgrounds, and they give you the number of events expected from signal and backgrounds and all that, and this is all public, so you can get the background numbers and the signal numbers they use, and you can calculate for your own model your confidence level and try to make the same plot. So that's what we're going to do. What do we have? We have contributions to these things. So we have many topologies. For instance, as we have this same vertex with W, N, and muons, this is like the same diagram they were looking for in the CMS search. We have a contribution from one operator generated at tree level and one generated at loop level. So every vertex here can be or blue or violet. Okay, we have that. But as we have these four Fermi operators, you can have an initial quartz that gives you the jet from BBF and the muon, and also this thing. But you can have also the combination with AW and the four fermion vertex. And you can have four fermion here to produce the N and four fermion vertex to decay. And you can also produce it here and put a W that will give you the jet, a pair of jets. So it's not exhaustive, this list, but this is what I managed to draw for this talk. Okay, so we have all these contributions. And the good thing is, like, as in the CMS search, you don't need to produce the N on shell, in fact, to see the signal. And that's what lets you test higher mass values. So this is very interesting. And when I saw this search, I said, okay, I could do that. And it's not me, it's Agustin, but he can do that. So we do the thing. We have a model written in fine rules. We pass it to MATLAB file. We make on Monte Carlo events of our signal. We can test. Here I'm writing alpha, but it's alpha over lambda squared. And if you put lambda, the lowest, which is 1 TeV we're testing, you get 0.3, 10 to the minus 6. We'll talk about this later. These are really little, okay? But okay, you can change the mass of the heavy N, and you get your cross section, and then you produce your events. You pass them by Pitya, Delphis, and you replicate the analysis they make in the paper. So you make all the cuts they do. That's our thing. Now, if you're interested in this, we can talk about this, because if not, I'm not going into the text because it's boring, but you have to do it. You have to be sure that you're doing the same things they did, and then you're left with a number of events in the signal region, and then you can put your bounds. Okay? Carolina.
The section is calculated considering all the operators.
Yeah.
Yes. And what is the enhancement of this scenario in which you consider all the operators regarding to the standard model calculation? Of
There's no standard model contribution, because this is less
necessary.
than number violating signal, and that's what's good. You have other backgrounds. You have backgrounds from non-prompt lepton that can go W plus minus, that go other things, WZ, all that. That's what they do in CMS. They consider all that as background, but you don't have pure standard model background. And this is why we like lepton non-violating signals. Okay? Because there's no pure standard model contribution. That's safe. If you don't have that, well, you have a non-reducible, irreducible standard model background, and then you have to deal with it. But here I have you have no standard model contribution. So when the coupling goes to 0, that's the standard model. Okay, you don't produce this. Okay, so you do the cuts. There are many interesting things here going on. You have this step-and-fold variable that helps you distinguish how much you get these quarks, these jets from the BBF here. These BBF jets, they have to be open in They have to be far away in the detector, but not that much. And you can play with all that. So this BDF topology is very interesting in itself, but I'm not going to discuss that right here. But okay, you can follow all the search, do everything, and you get your number of events, and you can make your plot. So it's the same plot as they did, but now I have mass and the couple. The Wilson coefficient, the lambda squared, and this is what I get. So this is from like last week. So that's why I have this. Maybe this will change because we're just working on it. But this is the first results. It's really in Spanish because it's from Agustin's thesis. So we get this. Here we get more events than those which are compatible with the measurement in CMS. Here we get less. So from the line down, this parameter space is allowed. So alpha can be as low and the mass can go through. This is hard. This is crazy, but we did it because you can play with that. There's no problem with it. So you can make the simulation for each point in this parameter space. You choose a mass, choose a coupling, and you make 100,000 events. You calculate how many signal events you get in your signal region, and then you say, okay, is it above or below the number allowed by the statistics?
So the line,
this is forbidden.
I mean, the line you have there is the bound that CMS put.
Yeah, okay. CMS puts on our theory.
Right, yeah.
Okay, so, but it's right. Produced in this way. So I have every point, you know, here, there's a point. Do I get more or less events than compatible with CMS? With their backgrounds and with their number of observed events in the signal region.
Exactly.
That's why we call it a recasting. Because it's not that I don't have an equation to translate this curve to the other curve they have. I am making the simulation for every point, and I'm putting the bound on my theory, given their numbers. Not their signal numbers, their background numbers, and their observed number of events. Okay? That's why it's called recasting. Okay? And you see here, they were getting like values which are higher than those that we were seeing in the first plot, and I get much lower because here is 2 times 10 to the minus 6. So like the bound for the agnostic scenario gets much lower. So it is wrong, okay? Or it means that if you get this lower bound, so here you have the bands on the spec and choosing and all that. But the thing is that I have discarded the mixings, okay? But I get a bound on the kind of couplings I have in the agnostic scenario that is much lower than the couplings were. So this is kind of okay. I should redo the calculation with the mixing. Okay, that's it. So that's my conclusion.
If you start to see, you start to turn off each operator. Do you expect that this line will go up, or?
Well, we can make a comparison with this diagram, which is given by this operator, because this is exactly the same signal they are talking about. Okay, so I expect that if I only let it on this operator, I will get the same value, mostly, because it's like the same physics, the same topology involved. Okay, but the other gives a contribution that is higher, and this is why the bound comes down in the plot.
Can you show me again the figure?
My figure? Yes.
So what you're saying is that
if I turn on one operator, this line will start to get higher.
If you were in the yellow zone, it means that CMS should have seen more events, but they didn't.
They didn't. As they didn't, the confidence level limit, you know, it's a calculation that gives, it says, if you have this background and if you measure this number of events, how much signal is compatible with a fluctuation, a statistical fluctuation of the experiment. So that's the meaning of the confidence level. So you say they have one background point for their signal, mass, and so they have the tables. You can see they got, like, I don't know, 100 events of signal. They get 120 events of what they call background, and then you can see if your signal number is they measure like 111. So, and then you make the calculation for each point and say, am I above or below that? You make a plot, a 3D plot, then you cut it. This is a contour plot on the number of allowed signal, compatible with a fluctuation of experiment. And then you do it. So if I have less operators on, I will have less events. So this line will go up. That's it. So by treating everybody agnostically and democratically, I can have more signal events, but in comparison with what I neglected, now I should say, okay, no, the real treatment should be taking into account the mixing and try to separate both contributions, because the mixing is there, and well, you should try to do it better. But for the agnostic theory, I have this one. So this is my claim. This is what I get. So maybe my hypotheses are too strong. Yeah. Okay. So, but this is new, and we're just working. What is something I'm proud of is that we could make the recast. So that's the hard stuff. So our team was very sharp, working like 2 years from now, and it's done. So I'm very proud, and that's it. So what did we get in before for other sensitivities? So we had done works for fluid colliders. So we can compare with that. For instance, this was also in 23. We did it with my former students. We studied a signal which is easier to generate and to do the Monte Carlo stuff and all that. That is proton electron. So this is the future LHEC. You know, if they change one beam from proton to electron, that's something that they're planning to do, or they were planning to do at some point. And you can see this kind of thing, that you have a lepton flavor violation signal, just giving mu minus, but you can also have a lepton flavor and number violating signal, searching for mu plus. So we have contributions to this, and we have done like the same exercise, saying, okay, you can put a mass, put a coupling, and then you do the same thing, but here you get your cars asking yourself, which is the number of signal events compatible with no signal in the experiment. It's like, if the experiment measures what they expect for background only, that's how you get those curves. So those are sensitivity prospects. That's what you make when you get prospect, because you don't know the actual measurement, because the experiment doesn't exist yet. So that's sensitivity prospects. And we have things that is for much lower mass, of course, because this is lower energy, but we were getting this like 0.5, so this was already little, okay? But now we have like the first real experiment results. So we put this lower masses, and these were the bounds we got as exclusion limits for the agnostic scenario. But there's one thing I haven't told you, that in my first year, I always had considered a bound, numerical bound, on the value of the vertices that contribute to neutrinoless double beta decay. Because you say, this kind of operators, this one with electrons in the initial state, they would contribute to neutrino beta decay, which is something that doesn't happen. So we can put a calculator like a bound that is like the coefficient, just the alpha, not the lambda. If it goes 3 times 10 to the minus 2 square root of the mass of the n over 100 GeV, so something like that. So when we did these calculations, we imposed that bound on the production vertices because you have electrons in the production here. So we did the numerical calculation saying, okay, these operators with an electron field cannot have couplings bigger than this in order to get prospects that are sensitive, but that are like feasible. But we didn't do it in the LHeC because we can consider them, but we said, okay, let's be really agnostic. So that's also something that would, if we do it numerically, that this would throw the line a bit more higher. So that's the thing. So in order to make them really comparable, we should put the same bound. Okay, well, we're gonna try, but we have to simulate all the events again. So that takes time, you know. Okay, and we have done something for E plus E minus with this kind of also very clean signal, which is that you produce a light neutrino and a heavy neutrino, and this heavy neutrino decays into mu plus, mu minus, and neutrinos. And you can also have this same production, but then the heavy end decaying to mu, but a pair of jets. That also can. So we studied the prospects for both channels for an energy that was intended to be for the ILC, this international linear chloride, that this won't happen. So for FCC, for instance, the energy will be much less. So we won't be able to test masses so high, but you could also try to see the prospect for FCC. We haven't done it, but it's like on the list of things to do. So here we were getting, depending on the luminosity of these experiments, how much events they make, you get different things. So this is it. This is my last year. Still, this was published last year, and well, that's it. So this is the end of the talk. And now I want to ask you, what do you think? And if you think something and you think about it later, you can let me know. So you write me an email, and I'm gonna say thank you for your hospitality. I have no conclusions because I have told you all my thinking through the talk. So thank you very much.
Thank you very much, Lucia, for the very nice talk. Question from the audience? Any questions?
Anybody wants to join? Work with me?
I have a question.
Yeah.
Your agnostic, let's say, model.
Yeah.
Maybe it's a little bit too demanding, right? Because I would imagine if there is a, say, I'm looking for, beyond the standard model, say, explanation of the neutrinos.
Yeah.
And to assume that all these extra operators are kind of comparable.
Yeah.
It sounds a bit.
It's too much.
Too much.
Yeah, I agree, totally. But it's like we were. It's choice you make. Yeah, of course. So you can turn them on once at a time. So that's what people usually do, and that's like the usual approach.
So my question is, can you simply reproduce this analysis by using only one of
the
operators?
Yeah, I'm on it. But yes, that's the next. But for operational reasons, we had this UFO built with everything on, and we were like playing with it. So we did it in this scenario, and then we should like try to be able to choose operators and fix the values and all that. But you know, like when you're building the model in Finance, that's kind of tough. So that's why we're playing with this, because it's easy. It was easier for us when we first thought about it to put everything on and the same value, and that's it. But I'm working on making this kind of thing doable, so that, and there have been, I haven't cited them because I didn't have time, but there have been people making plots like this, so translating all these bounds. So Enrique Fernandez Martinez, and people from Spain, and well, that there's one paper that I haven't cited, but you can go here and see cites them, and that's it. So they have made like the translation of every bound here for operators once at a time, but for masses up to 100 GB of the SMEFT operators. So you can find that, and you can download the bounds and all that. So as that was made, I said, okay, I tried to search for higher masses with another approach, which is like, yeah, it's too much, but this does. Thanks for doing.
Yeah, and I guess that you consider this agnostic scenario because you want also to explore interference.
Yeah, that's the first point in my list. Yes. My list. Where are you? List? Here. Yeah. Where? No. List. Here. So that's it. You have all these things going on at the same time. So for me, it's important to say, okay, how can you ensure that you have only one operator contributing when if you flow the renormalization group, they mix. So that's a theory. That's for me, that's the strongest theory reason. It's like, if you have only one operator, how can you ensure that? So it's always something that I always think about. Like, okay, you turn one at a time on, but they mix. So you should try to be more careful with your predictions, given that you're using like real experiments that are going on. These are real bonds. The bonds I get for LHeC are bonds that are taken. It's as if they were taken from experiments. So that's for me, that's the strongest theory reason. I want to enable interference, and this is a play that lets you produce them and decay. So when people are talking about like displaced vertices coming from these long-lived ends, so if it's too long-lived that it doesn't decay, you don't produce it. So if you have the same operator in the production and decay, you cannot play with all that richness that people have been exploring here, like Juan Carlos have done things, Joanna Coutinho, they have been exploring those things. But you need to get some interplay between production and decay in order to have richer phenomenology. So that's the thing. And then this is like having everything into account. Well, the easiest way to do it. Then you could choose like groups of operators, not one, but two, and things like that. So that's something you can do. So there's much parameters placed and to explore. And okay, we will keep on working on that. But for me, I'm glad that we did the first bounce from a real experiment, because there had been no real measurements done for the theory, and well, maybe with some help we get them to do the recasting, the collaboration. Atlas also has a search that is similar, so if NRSMET survives as an idea, you can play more and more with the operators and see which physics it gives you. So it's interesting.
Lucia, in your analysis, have you considered also the computed the prospect for the future LHeC, for the high luminosity LHeC?
No, not yet.
Not yet. Maybe they,
so this is the first calculation for LHeC that we've done, because it's difficult to make this intention. So we have managed to do this. And we chose to make a recast of an existing search, but yet high luminosity LHeC is also on the list. I need students or people who want to work with me. So I'm open. You write to me and tell me, you let me know. Okay?
Okay, I have a last question. Well, from this plot, you cannot say that you are setting strong constraints in the Wilson coefficients or in the new physics scale, because each region of this can be fit for value of lambda of C.
Of course, you can choose alpha 1, and this will give you, no, these are order 1 couplings.
Yes.
If you get lambda to be 1 TeV. So lambda 1 TeV is order 1 coupling. Not that far.
Yeah.
Okay?
Yes.
The thing, what is worrying to me is that I had decided to neglect the mixing, and it's like of the same order of magnitude. That's what is like. That's what I don't like in the end.
Another question. How you consider in your analysis, for example, in the E plus E minus with this diagram that you show for the diagram that we have in the W chain and mu plus mu minus in the final state and the chain of the active neutrinos, I think one of your slides that has the similar topology with neutrinos without beta decay. This one? Yes.
Yeah.
For example.
But it's you don't have this in E plus E minus. Well,
I was thinking E plus E minus. I was thinking E plus E minus, and maybe having you had some, for example, to his double model, you could have also the Charkis chain instead in addition to the W chain. So maybe they could provide some lepton number violating signal.
Well,
the effective operator for the it will be not a standard model effective field theory approach, but
many UV completion for UV complete theories that could give you this kind of sign. But
not from the point of view of proton-proton collider, but E plus E minus collider. So it could also be.
I guess you can have that. As you know, I'm not an expert. I do simple stuff. Well, not that simple, but simple from the theory point of view.
Well, if you had a E plus E minus collision, so forget the quarks.
Yeah, forget the quarks.
You have the E plus E minus going to W plus W minus.
Yeah, you can have E plus E minus, W plus W minus, and then
no, I was thinking in a process, not with the J in the final state, but a process that corresponds to lepton number violating final state in the electronic sector. For example, in the E plus E minus, to have, for example, neutrinos instead of the jet, of course, neutrinos instead of the jet, and charge Higgses instead of the WH boson. So in effective field theory, one can have, for example, a similar signal, but with a similar topology, but with neutrinos. And we charge lepton in the final state, so maybe some lepton flavor relating signal.
So it would be neutrinos?
Neutrinos, charge Higgses here, charge Higgses, and plus E minus. Some type of process that could be maybe provide some new physics.
And your E plus E minus?
But I'm not sure, So as this search for E plus E minus is not done, so you could try to play with that and then make a simulation. It would be here, but it's something.
So your E plus E minus colliding are the Q1 and Q2.
Exactly. And instead of the W, the charge Higgses, and maybe 2H double model extension with sizable coupling. I mean, an extra Higgs doublet that has a very small bed and that participate, for example, in type 1 scissor realization. It could be maybe some signal.
That could give you some. what you need here to play the game is you have to write an UFO to give to Malgas. So if you can build your model like in fine rules, which is the program that lets you write the Lagrangian all the vertices and passes it to MATLAB, and you can simulate it in MATLAB, we can work. Because I know how to do the events and the statistical analysis, which is easy, but you have to know how to do it. So or anyone, if you have an idea or whoever, you don't. Okay, but now you can play with it. So it's like something. It's an open door. But that's like the ingredients you need. You need to know your Lagrangian, and with the Lagrangian, you can do all the stuff.
So LEP should have.
LEP should have seen something like that, because there are same sign dileptons with missing energy. Maybe you can find something. Yeah.
Yes, with antiathesis.
Yeah, of course. Well.
Any more questions for the audience? Comments? Questions?
Thank you very much.
Thank you so much, Lucia, for the very nice seminar.
Good. Bueno, muy bien.
¿Y cuánto más?
Y me voy el viernes.
¿El viernes?
Sí. Bueno, pero hablamos. Voy a ir a la HEP. ¿Vas a la HEP?
¿No?
¿Vas a la HEP?
Sí.
Bueno, vamos ahí. Voy a contar esto.
¿Y a SILAFAE vas también?
Sí, obvio.
Sí, yo tengo que ir a SILAFAE, pero tengo un problema que tengo que organizar acá justo la semana que viene la reunión de SWG. Entonces, no sé cómo
no sabía que había quedado tan pegado.
Sí, claro. Y claro, casi una semana después.
Pero bien, nosotras vamos a hacer.
Sí, invité a Yossi Nir, que aceptó ir.
Claro, sí, es verdad, sí, esta semana anunciaron. Sí, va a estar bueno, ¿no? Y va cajita, va a estar bien.
Sí, porque allí
no, está bueno. Sí. Hay que decir a FAE, ¿no?
No sé de qué
de gente famosa que va al simposio latinoamericano de física de altas energías que este año en Bogotá, en noviembre, a fines de noviembre. Ahí va. Bueno, bien, no sé si estamos grabando, la gente puede estar aburriendo. Vámonos a trabajar. Muchas gracias por su atención. ¿Cómo es esto? ¿Lo vamos? Daniel, ¿estás ahí? Short question.
Audio is connected, but I don't know if there are people there. There are two participants. We could check there, but I don't know if the Daniela is there. It's 15:36, so it was some time ago, but
no, yo creo que ya no.
Se fueron, parece.